Okay, let's say I hand you a challenge, and it's a big one. I'm talking a puzzle of absolutely staggering proportions, with a massive budget and the fate of an entire country's infrastructure resting right on your shoulders.
Here's the budget. 1 billion euros. And that's not a one-time thing, that's every single year. The stakes? Well, they couldn't be higher. Every single decision you make, every cent, has to count.
So here's the puzzle itself. You've got 38,000 kilometers of railway under your control. The problem? Demand is about to explode. It's going to grow by over 40%. You obviously can't upgrade everything. So, where do you put that billion euros? How do you figure out where it's going to have the biggest impact, the best result? I mean, where do you even start with a problem that big?
And this isn't just some thought experiment. Nope, this is a real-world problem that Germany's railway network had to tackle. It's actually the perfect case study for what we're talking about today, the hidden science of making the best possible choice.
So let's just look at the numbers for a second. The network is huge, and that gap between what it can handle now and what it's going to need to handle, well, it's massive. And with that budget, the goal isn't just to throw money at the problem. No, the goal is to spend it in the smartest way possible, to maximize profit. You have to pick the right projects, and you have to do them at the right time. It's a truly colossal decision-making problem.
All right, so how on earth do you solve a puzzle this big? You don't guess, you definitely don't just go with your gut feeling. You use a powerful systematic framework from mathematics that was designed for exactly this kind of challenge. In that framework, it's called optimization. And listen, this is key. It's the science of finding the best solution, not just a good one. It's all about methodically sifting through every single possibility to find that one perfect answer that hits your goal and follows all the rules you've set.
You know, any optimization problem, no matter how complicated it seems, can be broken down into 3 core parts. First up, the objective. That's your goal. What are you trying to maximize or minimize? For the railway, it's simple. Maximize profit. Second, you have your variables. These are the choices you can make, the levers you can pull. Like, which upgrades do we build and when? And finally, you've got your constraints. These are the rules of the game, the things you have to obey, like, staying within that 1 billion euro budget.
Okay, so once you've framed your problem with those 3 components, you need to pick the right tool for the job. Because, and this is really important, it turns out that the type of choices you're making can totally change how hard the problem is to solve.
Let's look at 2 big categories. On one side, you have what are called linear problems, or LPs. Think of this like adjusting ingredients in a recipe. All your choices are continuous. You can add a little more of this, a little less of that. These are, relatively speaking, pretty easy for computers to handle. But then you have mixed integer problems, or MIPS. These are different. They include discrete yes or no decisions. Things like, should we buy this new machine or not? And these are the really tough nuts to crack. Computationally, they're what's called NP-hard, which is a fancy way of saying the difficulty can just explode as you add more and more choices.
And that brings us right back to our trains, doesn't it? The railway puzzle is a massive mixed integer problem. For every single potential upgrade, the choice is binary. It's a yes, we build it, or a no, we don't. Now multiply that by thousands of potential projects, and the number of possible combinations just becomes astronomical. Absolutely mind-boggling.
But here's what's so incredible. This whole framework, objective, variables, constraints, it's not just for trains and budgets. Not even close. The very same logic can be used to solve puzzles in a completely different field. And honestly, it's kind of mind-blowing.
Because this exact way of thinking, this same mathematical toolkit, can help us tackle one of the greatest puzzles in all of biology, actually reconstructing the evolutionary history of life itself.
So the question becomes, right, if you've got the DNA from all these different species that are alive today, how do you work backwards from that? How do you figure out their common ancestors and build the most accurate tree of life possible? Well, the answer actually lies in a classic optimization problem called the Steiner tree problem. The idea is actually pretty simple. Imagine you have a set of points that you absolutely have to connect. We call those terminals. The goal is to find the shortest possible network that connects all of them. And here's the cool part. You're allowed to add new junction points. We call those Steiner points if it helps make the total network shorter.
And this is where it gets so elegant. In biology, what are the terminals? They're the species we have today. The Steiner points, the new junctions we're looking for, those are the unknown common ancestors. And the cost or the length of a branch? That's the evolutionary distance, basically the number of genetic mutations between 2 points. So the objective is to find the one tree that connects all living species with the minimum possible total evolutionary cost. See, it's the exact same logic, just applied to a totally different, amazing puzzle.
I mean, that's just an incredible application, right? But it brings up a really important question. How do you actually translate these logical ideas into the cold, hard language of math that a computer can actually work with? Well, that is the art of modeling.
Think about a really simple human rule, like either or. In a project, you might have a rule that says you have to do either this or that. Simple for us to understand, but how do you write that down in a way a computer gets it? How do you turn that into a mathematical constraint?
Well, you use this wonderfully clever modeling trick. It's a real trick of the trade, and it's called a Big M constraint. It's seriously one of the most common and powerful tools that people who do this stuff have.
So here's how this little bit of magic works. You create a binary variable, just a simple on-off switch that's either a 0 or a 1. Then you use a really, really big number, we just call it M, to link that switch to your two either-or rules. So when the switch is set to 0, the first rule gets enforced, and that giant number M basically deactivates the second rule. Then you flip the switch to 1, and the exact opposite happens. It's such a simple, elegant way to tell a computer pick one of these two things.
So, from billion-euro train networks all the way to mapping the tree of life, you start to see that these techniques are kinda everywhere. Optimization isn't just some abstract thing for academics. It's like this invisible engine running in the background, quietly shaping so much of our modern world.
I mean, it's used to design the airline routes that get you from A to B. It's managing air traffic control in real time. It's the brains behind financial models trying to balance risk and reward in your investments. It's used for super complex engineering problems like figuring out the best way to route thousands of pipes in a power plant. Heck, as one of the sources we looked at pointed out, you could even use it to figure out the mathematically fairest way to settle up the coffee fund in your office.
But it's important to remember, and there's a great quote from one of our sources that says this perfectly: there are good and bad models. There are no recipes, only experience. This stuff is as much an art as it is a science. Building a model that really, truly captures a messy, real-world problem, that takes skill. It's not just about following a recipe from a textbook, it's all about experience, about trying things, testing them, and making them better.
So today, optimization is the tool we reach for to find the best answers to some of our most complicated puzzles in logistics, in finance, in science. Which really just leaves one big question, doesn't it? What impossible problem should we point it at tomorrow?